Hey everybody, Mike here. This is how I got a problem with squirrels eating near the bird feeder. And the way I deal with that is I just scare them off with electromagnetic radiation. Yeah, that's how I do it. See, that's right there. That's what we call in science electromagnetic radiation. So I just kind of don't hit them in the eye. But, hey, okay, it doesn't work that good. But, and there he goes. Oh, he must have cut a reflection. But anyhow, I'm going to keep working on this. But in the meantime, let's go talk about electromagnetic radiation, which visible happens to be part of. Okay. Anyhow, I'll see you soon. Well, hey everybody, hey, Mike here. I did get the squirrel to eventually go away from the climbing the bird feeder, but yeah, I switched to golf balls. That's a particle wave theory going on there. But anyhow, look, here we're going to talk about what they call light radiation or electromagnetic radiation. So you'll sometimes hear it called light. But the thing is, you can't see all kinds of light radiation, so we'll talk about that when we talk about the spectrum next. But any kind of wave will have a wavelength. So let's use some simple concepts here. You go splash in the bathtub and you splash at a regular rate, you'll create a wave. There'll be a certain distance between those waves, and the more energy you go in the bathtub, and if you put more energy in, there'll be less distance between the waves. Light energy is just like any other kind of wave in water or whatnot, like you splashing in the bathtub. It has a wavelength. A light wave we call a photon. Sounds Star Trek-y. And so we have the symbol lambda, which is the wavelength. That is, it's a length. It's in units of meters, nanometers, micrometers, whatever the kind of radiation might be. And here I've shown it's basically peak to peak, or it could be valley to valley. It doesn't matter which way you do it. There's a certain length that's reproducible in electromagnetic radiation. Also, it travels at a very, very fast speed, which is called the speed of light, which is 3 × 10⁸ meters per second. So let's think about that. How fast is that? Well, 100 meters is about a football field. If you cut the end zones off, they could be Cincinnati Bengals football fields. So anyhow, but if you have a football field, it's about 100 meters. Therefore, this would be 3 × 10, divide by 10 to the 2. This would be 3 × 10 to the 6 football fields. That's 3 million football fields every second. That is haulin', gang. And therefore, you also have another way to describe electromagnetic radiation. This is the third way to describe it. Actually, one of 4 ways, but we'll talk about energy next, is the frequency. How many waves or cycles per second? Now, one unfortunate thing is you'll hear this also called a hertz, but since we just say, hey, things per second, that's like 1/seconds or inverse seconds. I won't call it a hertz because that makes you have to remember what a hertz is. And so the kind of anti-memory thing that I like to do is to just call it an inverse second. And nothing against hertz, but it's just too many things named after people where we really are just naming something it's an inverse second. So all of these 3 things are a sort of property of electromagnetic radiation. And now let's talk about the spectrum of how electromagnetic radiation occurs in nature. So what I've done here is I've drawn a sort of line of energy, or you could look at it like increasing wavelength. A wavelength of this thing I have here below is increasing as you go to the right. So radio waves have longer wavelength than do, say, X-rays and whatnot. And for our purposes, we're going to focus around the middle of the electromagnetic spectrum, because it turns out in the next video we're going to find out what makes light is atoms and the electrons in those atoms. So now, increasing energy goes the opposite way of wavelength? Yeah, okay, here, think about it. Go splash in the bathtub. The more energy you put in, the closer the waves will be. Okay, I'll wait for you to go and do that. Everybody go, splash in the bathtub, and then come back and watch the rest of the video. You can splash with someone else if you want it. Okay. Okay, so did everybody notice that when you splashed harder, you had the wavelength was opposite that of the energy? So to the left is increasing energy, which parallels frequency. So the closer the waves are, the more energy is in the electromagnetic radiation, and the tighter the waves are, the more waves per second. Now, here's the thing. If I'd have drawn this properly and I didn't want to expound upon the visible range here is a tiny, 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 tiny sliver of radiation that you can see with your eye. Everything outside of that is not visible. We can't see ultraviolet. I know it has a color in the name of it. Can't see it. Can't see infrared. So visible is broken up into the colors of the rainbow. So how do you remember the colors of the rainbow? Real simple. It's a guy's name. Roy G. Biv. Red, orange, yellow, green, blue, indigo, which is kind of like a turquoise, violet. And now here's the thing though. Infrared means lower energy than red. So you actually, the way I've written it, you have to write Roy G. Biv backwards. Red, orange, yellow, blue. I got ahead of myself. Roy G. Biv. Green, blue, indigo, violet. So it's like Vidyor, but you know, just because I happen to have written it where wavelength is increasing to the right. Now, how do you remember that? Red is next to infrared, lower energy than red. Ultra, higher the energy than violet. So you should be able to recreate this whole thing in your mind. And I'm going to give you two kind of even numbers to remember, and that is the wavelength here of the lower part, lower in wavelength, higher in energy, and the higher wavelength end of the visible spectrum. It's about 400 to 700 nanometers. Nanometers. If you really want to get into the nitty-gritty of what separates each color, you could say it's about 50 nanometers in between each. And so if someone said, okay, this is between 500 and 600 nanometers, it's probably bluish green. And if it was something like 650 nanometers, you say, oh, that's got to be red. And so we won't really have to do that much of that in this particular course, but that's how you construct out of nothing but your knowledge of the name. And 400 nanometers to 700 nanometers is the visible spectrum. And now, by the way, keep in mind, in wavelength terms, infrared is way huger of a range than visible, and so is ultraviolet is huge. So it's a way bigger range than 300 nanometers is ultraviolet. As a matter of fact, they split the ultraviolet into different regions, like A, B, and C, depending on which part of ultraviolet it is. Heck, even X-rays, if you go over here, they have what they call soft and hard X-rays, depending on how far along the energy scale they are. Then you get into really crazy stuff like gamma, because that's what invented the Incredible Hulk. Not really, that's fantasy. Radio waves, actually they tend to do in frequency. Megahertz is FM and kilohertz is AM, and then you have longer radio waves like long, you know, like ham radios and stuff, and then you even have microwaves, which sound like they have a lot of energy, but per photon they really don't. It's just that when you're using your microwave oven, you're just slamming your food with lots and lots of photons, and so they add up, and that way there's a lot of energy going into your food. If you ever go and take apart a microwave and look at the coil that generates all those photons, it's a gigantic one. So let's go do some number crunching next. We're going to go and try to interrelate wavelength, energy, and frequency in a practical way, which we'll need to do for our next video where we talk about atoms. Example problem, whoop, whoop, example problem. All right, here's an equation. It was given to you by the universe. There's no need to really memorize it. Go write it on a piece of paper somewhere. And that is that the speed of light is the wavelength times the frequency. And now let's do this. We've been talking about units kind of help you solve problems. The units of C are meters per second. The units of frequency are 1/seconds. And so the units of wavelength are meters. Uh-oh. They gave us an example of Mike's squirrel repelling laser pointer, which, by the way, I bounced off a cloud once. Pretty cool. Green is the color range of 520, and by the way, green is also the easiest for your eye to see, for whatever that's worth. I don't know, ask a biologist why that is. So it has a wavelength of 520 nanometers. What is the frequency? So what I'm going to do is write down the magic equation, our main weapon, C equals wavelength times frequency. To solve for frequency, I'm just going to divide both sides by wavelength, so that on the right side we cancel it. Frequency equals C over wavelength. Now, I'm going to go over here and do the wrong thing. This is going to be a special place where I go and do the wrong thing. Don't do it. The wrong thing would be to say, okay, 3.0 times 10 to the 8th meters per second divided by 520 nanometers. What's wrong about that? Well, meters don't cancel nanometers. So what I've got to do is I've got to convert my wavelength to meters. Then I can use this equation. That would be great. And so very often you need to convert your wavelength into nanometers. Not a big deal, because we all remember from way back in the beginning of the course our metric to metric conversions, and that is that there are 1 nanometer. I like to put a 1 on the bottom. There are 10 to the minus 9 of a meter. You could put 10 to the 9 on the bottom and 1 on the top, but I like that because it's now making me not have to use my calculator. 520 times 10 to the minus 9 meters. Okay, let's go and make this a proper use of scientific notation. 5.20 times 10 to the, well, I got to move the decimal point twice to make that number smaller. Got to make that number 10 to the 2 bigger. Or you could just do it on your calculator. That is the wavelength in nanometers. Now we're going to go plug it into the equation like we wanted to. Frequency equals speed of light, 3.0 times 10 to the 8th meters per second, divided by 5.20 times 10 to the minus 7 meters, Mike. Meters. I wrote nanometers. Meters. Now let's stop and pause here. 10 to the 8th is, you know, that that's 100,000. 100 million, excuse me. 10 to the 9 is a billion. So we got 300 million divided by a tiny number. We're going to get a big old number, folks. So 3.0 times 10. Remember how to find your scientific notation is, for me on this calculator, it's the double E. So 10 to the 8th divided by 5.20 exponent button times 10 to the minus 7 equals 5.77 times 10 to the positive 14. Units are now inverse seconds, or hertz, if you want to call it that. Now, think about it. A photon got tiny, tiny wavelengths, nanometers. Nanometer is a billionth of a meter, and it's going 300 million football fields a second. That's a lot of waves per second. That's why frequencies are usually huge. Even the long wavelength stuff like radio waves and like on your radio, megahertz, that's 10 to the 6th. Kilohertz is 10 to the 3, that's 1,000. So, you know, you still have frequencies are usually big numbers. All right, let's talk about how we can relate frequency to energy with another example problem. All right, here we go again. New equation. This is our second equation. Energy is a constant called Planck's constant, if you really is a constant times frequency. So you think about it, the more energy you put in, the greater the frequency, because the waves get closer together. And so if you look at this, energy, hey, joules. That sounds familiar. Energy's in joules. This is actually got units of joules times seconds, and now because both sides of the equal sign have to be the same units, this would be 1 over seconds, so the seconds cancel out, and it's joules on both sides of the equation. So, but uh-oh, here's energy. They want wavelength. So I'm going to have to recall this equation to solve this, but I'm going to take it stepwise, and I'm just going to solve for what I can. I have H, I have energy, and so I'm going to solve for what I have, which is frequency. Now, frequency doesn't give me the wavelength, but I can then take the frequency, and using the equation we just used before, I can find the wavelength. And then if you can find the wavelength, you can find out where does it lie on the electromagnetic spectrum. Is it in the visible range of 400 to 700 nanometers? Is it outside of that range? Which side is it? So is it higher, lower? We'll find all that out, but just take it one step at a time, and I'm going to just fight the battle I can, which is I got E, I've got H, I can now find frequency. So E equals H times frequency. And you might want to label these things as you read them. Say boop, 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 like a computer. That is an E. And then you have an E and an H, and you could just solve for the one that's missing. It's half the battle with these things, folks. Divide both sides by H. Frequency is E over H. And then I should have the right units. That'll keep you straight. So 1.65 times 10 to the minus 19 joules divided by Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. And I can tell I'm doing the right thing because I have the proper units of 1 over second. And I can tell I'm doing the right thing because I'm going to get a huge number, because frequencies are usually huge. 1.65 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34 equals 2.49. I'll do it in 3 digits. 2.49 times 10 to the 14. Inverse seconds. Not there yet. We got to take that number and use it in the other equation. C equals wavelength times frequency. the problem wants wavelength. So I'm going to solve for wavelength. Wavelength would be what would happen if I divided both sides by frequency. Kind of like the opposite of what I did in the other problem. So divide both sides by frequency. And now we have a frequency. So we'll plug it in, 3.0 times 10 to the 8th meters per second, divided by our number we just calculated, 2.49 times 10 to the 14. And let me tell you, folks, once in a while you just get lucky. Because I don't feel like hitting my calculator button too much. And I don't have to, because I know that I got a number that's bigger on the top than the denominator. And so you know what I'm going to do? I'm going to go and say 3.0 divided by 2.49 is 1.20 times 10 to the powers of 10 subtract minus 6. 8 minus 14 is minus 6, and that is meters. Now, theoretically, I've solved the problem. But I don't know if I can easily really know what the second part of the answer is. What type of light energy is it? I'm going to go and convert this to nanometers so I can find out if it's between 400 and 700. 1.20 times 10 to the minus 6th meters, nanometers. 1 meter is 10 to the 9 nanometers. This way I can just add together the exponents. 1.20 times 10 to the negative 6 plus 9 is 3. What's 10 to the 3? That's 1,000. What's 1.20 times 1,000? 1,200. Now, where is that on my scale? Where is that on the scale of the electromagnetic radiation scale? That is now greater than 700. It's in the infrared. So it's a larger larger wavelength than it is visible. And because it's kind of close, and I told you that all those other ranges are way bigger than 300 nanometers, like visible is a tiny, tiny sliver. If I'd have done this diagram right and I knew I didn't have to write Roy G. Biv, I would have made this like, you know, like that. But I couldn't have fit that in there. Couldn't have fit the word visible in there is why I didn't do it. So that is infrared, which by the way is the same energy as radiated heat. And that's another thing. We're now talking about transmitting energy through waves. When the sun hits your face, that's energy, and that's why sometimes you feel warm, you know, when you got light on your face. That's because there's energy in there, and sometimes it's dissipating to heat, and that's why you feel that. So we got these different 3 representations of a photon. We've got wavelength, and we can go back and forth between wavelength and frequency with this equation, C equals wavelength times frequency, and of course C equals 3.0 times 10 to the 8th meters per second. And we can go back and forth between, and we can go back and forth. Yeah, that makes a good point. Bridge out. There's no direct relationship between energy and wavelength. You've got to go and convert your wavelength to frequency, or in like the last example, convert your energy to a frequency and then your frequency to a wavelength. And the way to do that would be through E equals Planck's constant times frequency. And the Planck's constant is 6.63 times 10 to the minus 34 joules times seconds. If you're a student in my class, I don't make people memorize this stuff. I say, go make a formula sheet. These are tools. There's no reason to memorize constants. The universe gave them to you. They're free. And so, and then technically, speed of light's a little bit less than 3 times 10 to the 8th meters per second. And that's, by the way, through vacuum. If you talk about through water, glass, it slows down through mediums, but it's close enough. And if it's through air, like my laser pointer, air is mostly vacuum. Gases are 1 out of 1,000 parts matter. And so those are kind of, you know, rough approximations, but it'll do for our needs. So next time, we're going to talk about, like, where does this stuff come from? Like, where does it all come from? It comes from atoms. And so, if we look at the light the atoms give off, then we could tell what the atoms are. What? Yep. So that's next time, folks, when we talk about quantum levels. Do some practice, and I got to go throw a golf ball at the squirrel, so I got to go. Take her easy. Bye.